So actually, been doing a little bit of Rust lately, like a few, maybe a dozen of hours. So that's not very much. A bit more if you count there's other projects I've been working on. But I'm still a noob, but I was really, really a noob at the time. And I wanted to write some code. It's actually a poker AI based on DeepStack, this research paper, DeepStack. It's quite interesting, but um, the complexity of the difficulty or not complexity of the DeepStack algorithm is already pretty high, and starting mixing with the language I'm not familiar with made progress extremely slow. DeepStack is actually implemented for a simpler version of poker called Leduc Hold'em, but they implemented in Lua and Torch, and these Torch is not supported anymore. I wanted to adapt it to Texas Hold'em, but Texas Hold'em is much more complicated, and in terms of the game space. So the stuff that they do in there, not directly applicable. And so initially I wanted to write in a language more popular, more familiar, um, like in Kotlin or JavaScript, TypeScript. But I don't think it would have worked very well because the um, the amount of data that is used by this AI algorithm that makes it impractical. So that's why I started learning using Rust. But again, Rust nearly knew anything, and that makes progress super slow. So then I switched to actually properly running Rust. So the the language has pretty good books here, right? So I did this guy with the book, of course. I did the course, and then I read this Rust by example. So I think altogether it gives you a good introduction to the language. So this guy definitely is a must read, um, because it gives you like an overview of everything that is part of Rust. This guy is a bunch of exercises that complement the book. This is even smaller in scope than the exorcism. So they would actually just take one part of the language and make you like give you some exercises about that. But it's all together actually it's difficult to see how you would write a more serious program, because in a bigger program you would have to deal with proper modules, separating the code into classes and traits, and then also into different files. And you would typically use a bunch of cargoes, because the language itself, and it's maybe one of the good things about it, is the language just is not very difficult to understand. Right? This book here, I don't know how many pages that represents, but it's not like it's less complicated than C++ for sure, because C++ has like insane dark corners of syntax, especially around templates, and it has also a very large standard library, and I think it gets bigger and bigger. Like if you consider a library like Boost to be part of C++, because essentially you can't do much without it. Then the library is really large. Um, in comparison, Rust Rust has this stuff, part of the design the language, and it has a standard library, which is kind of equivalent to the C library, but then it has a bunch of cargoes. So maybe it's pretty similar. The problems are similar because the cargoes, even though it's very simple to use them. I mean, again, comparing with C or C++, if you have a library that you want to use, then you have to read the documentation and the installation, all that stuff, right? And it would typically take you at least a few minutes, if not like a few hours, to figure out which dependencies you need and then how you build it, because typically you will build from sources. In Rust, the library, the standard library comes packaged with the installer, and you have this community database or community package manager, which has at this point 42,000 crates, so that's quite a lot. But building and using it is quite simple, to be honest, because you just have to put this guy here, and then the build system will download the stuff for you and build it, and it's all standardized. So sometimes it get a bit harder because you also have to add. They have features, so you have to put some options, but that's not really hard. The only thing I would say though that about cargo and crates is that since there are so many of them, it's not easy to know which ones are very good quality, and also which ones are not like interfering with others. And even like for relatively simple functions like logging, you would have many solutions. So for example, you want logging, this log thing. So you have this guy, but there's also env logger, I think. I think if you look for a logger, you're gonna see that there's quite a lot. There's logger, flexilogger. Okay, so there you go. But you have like really 9 pages of loggers. Okay, if you have 9 pages of loggers, so that's like 367 different loggers. That's quite a lot for just one function, right? But that being said, of course, for example, this one, the logger one, has been downloaded 24 million times. So it's, I would say, a pretty safe bet to use it. Okay, so that's one thing I would say about Rust is the packaging stuff, installation. It's very easy, and then getting started, pretty easy, right? You should just go through the Rust language page, and then install it, especially on a Unix system. Takes maybe like 2 minutes. And if you don't even want to install it, you can go through the playground and then try it online. But since it's so easy to install, I don't see why you wouldn't. Okay, that's the good news. The not so good news, you would say, is that the IDE is really not as easy to use as like for example IntelliJ, right? IntelliJ, if you use Kotlin is essentially a language that was invented by the creators of IntelliJ, JetBrains. So it's very well integrated with their editor, with the IDE. And then you start a project. You say, I want Kotlin. They create the Gradle file, which is kind of the make file. Then you run it, and you can directly put breakpoints and then debug the code right there. In contrast, Rust seems to be much more like C-like, where you bring your own tooling, right? You use your own editor, and if you want to debug, then you drop to GDB or like LLDB, I think is the name of the debugger for LLVM. See, I don't even know it. LDB, yeah, LDB. So it took me a while just to set up a project, like a simple project with integrated breakpoints in Visual Code. So it means like you have to find the right packages there, and more importantly, you have to set the debugging environment appropriately, and that was not documented. You had to go to search for it. It's not super hard. Rust debugger in Visual Studio, Visual Code. So the dev guys explain how to do this. But the stuff like that, I don't think it. I mean, it didn't work for me. What worked for me is this stuff here, right? So you have to do combination, and actually this is not exactly the one I wanted, because this is Windows, right? And then this stuff changes all the time. So of course eventually you get it, but definitely not as simple as an IDE. So most of the time I used print to debug, right? And frankly, that was not too bad. The one thing that works very well in Visual Code with the integration of the extension, integration of the language server, is that you would have some kind of annotation code. So for example, if you hover over a variable, it would tell you the type and it would tell you where it was defined, and that's very useful, because the type system is probably the most challenging part of the language. So I would say that tooling is not super good. Could be improved, but fortunately the language itself is very robust, quite simple to grasp, right? So that it makes things you don't need to see a lot to understand what's going on. What else I'm gonna say about this? Let's go actually through this language thing, right? So when you learn, we probably like read the book first, and so some examples are not bad, actually quite good, but I would say that if you are really familiar with a programming language, it will not be it will be a bit too simple. I think before you enter, but maybe that's by design. Before you enter, like particularly reading the whole thing, you're not really prepared to write a program. That could be caused by the fact that this is quite a different language than the ones like Java or like Python. You see these languages, the high-level languages, because one of the main reasons why you would like to use Rust is because it's a system language, right? And it's not too many of them, right? So I actually Google system languages before, because I was a bit curious, and the list, okay, surely there's not all of them, but nonetheless this is not a very long list, and these guys here, the first ones, are probably not in existence anymore. Right. Well, C of course is still there, right? But I never heard of like PL360. This guy. Oh, this is guy from Pascal, right? Uh, so lately, you only have these guys here, right? So even like the last one, Swift, which is the language for Apple development, it's debatable if it's a system language because I don't see you actually running operating system in Swift. It's more like you write apps. So Nim, I'm curious, but I never had a chance. So in terms of language that you would use actually to write operating system and stuff, it's still mostly C. Yeah, even C++, I wouldn't say it's a system language for writing operating system. Uh, so it's like most operating system, I even say it here, most operating system kernels are written in C. And I think that now Rust is like starting to try to have some operating system written in Rust. So the big reason why you want to use a system language is because you would have better control of your system resources. And system resources is by far the most common one is memory. But it's not only limited to that, of course. You also have to be careful about files, any kinds of operating system limitations you could have, right? But yeah, mostly memory. And typically there are two ways to address memory issues. Well, not issues, but memory management. One is through garbage collection, which is now most languages are doing that. So it started with Java, I would say. Well, maybe not started, but one of the first ones were popular ones was Java. And now nearly everything has like some kind of garbage collector. So even like D is garbage collected actually. Haskell garbage collected. Well, C Sharp, Kotlin garbage collected. Okay, tons of them are garbage collected. So that means that if you do want to have control over the memory you want to use and when it's freed, now you're back to C or C++ for the most part. But now we have Rust. So I would say needing a system language, which actually I think I did need one for my poker AI, is one of the main reasons why you would adopt Rust. And also because the system language is not the only thing that they want you to at least be aware of. So they are not going to hide memory management, but they aren't going to hide also error handling. Right? Error handling, like in C++, could be done through exceptions, but exceptions has a cost. Right? Exceptions, even if you don't catch them, you don't throw them, the compiler has to generate some code in order to set up the stack, in just in case you throw an exception, and be able to unwind and find the proper handler, the catch of the exception, the catch block of the exception. So that logic has a cost, and the philosophy of Rust, as a programming Rust, is that if either it's free, I mean like they have constructs where the implementation will have no cost as runtime. It's only a compile time complexity compile time, or you will have a way to see how to do it or avoid it. So what I'm saying is that since exceptions has a runtime cost that you can't really avoid, right? They would not use it. I mean, that's my interpretation, right? I'm not even like in their team or whatever, right? So again, I may be completely wrong. But I think this is kind of like what I picked up from reading all their stuff. And so this is why error handling is done for like actually you have to return a value that is an error, and then you have to check for it and so on and so forth. Right? So it's less convenient, but it's less like magical. Another thing that is in that philosophy is that you could actually compile a program in Rust without a standard library, and do have something very small. So that's very interesting if you are targeting a embedded device, which is like too little memory to even have a runtime, standard runtime. So which precludes using languages like Java, which has a pretty big runtime. Um, so you can compile without any of these like standard library. So no memory allocator, nothing. Right? And then you can bring the functions you want through crates piece by piece. Another thing that is very system language like. So I'm actually going through this. That's why I picked up this stuff. Oh, it's not object oriented, so you don't have this interface. Well, we have traits, they have traits, but it's not the same as like inheritance, and so there is no virtual table. Well, actually, there is a virtual table, but you have to elect for that, and they call it something like trait object something. But it's not like I've done lots of this code without actually. I maybe have used it once, um, and in practice, even like in languages that offer them, I think that using inheritance has become less and less popular, because actually it's a design pattern that is less useful or less powerful than delegation and aggregation. So they went through the aggregation / delegation like design rather than using inheritance. So you still have inheritance, but that's not a core, like that's not a selling point, the big selling point of the language. So it's not object oriented. Oh, let's see actually what it is. Let's go to Rust on Wikipedia. Multi-paradigm, yeah, concurrent, functional, generic, imperative, structured. Okay, so they don't even say it's object oriented. So I'm thinking it's definitely not their strong stuff, right? Okay, so multi-paradigm. Let's see what it means. Multi-paradigm means that wow, you have different things there. Concurrent, functional, generic, imperative, and structured. So functional imperative is they usually like they are put in opposition. But in most languages now are doing both, right? So the imperative is like 99.9% of language are imperative. So you basically, when you have constructs like loops, if, assignments, things like that, where you actually your program is like a recipe of actions to perform, that's imperative. And functional, like super layman definition. Functional is when you have like you have functions and then you combine them together, and specifically you have functions that return functions, right? So some of the aspects of Rust is functional, uh, and specifically around the map, the iterators, because for example map is a function that takes a function, or filter is a function that takes a collection and then a predicate, and then so it's a function that takes a function as a parameter. So that's like a functional style. And then even like this little guy, right? This bin up here is a function that takes a closure as a parameter, and then we do some standard stuff, and then to gather the arguments, and then we use our closure. So the pattern in the Gang of 4 pattern for that. I think it's called. Okay, I forgot the name of the pattern. Template, I think. I don't remember actually. I think it's template. Basically, you have a bunch of of standard behavior, and then you have a function that you can plug inside that customize that whole thing, right? So here you want to do a binary operation. So the common behavior is gathering the arguments, then you apply the function, and then you recover the result and you push it back to the stack, right? So the first step and the last step are common, and the middle step is where you can customize. Functional is very. I mean, personally, I really like functional languages. This goes beyond just having functions returning functions, but it's also the fact that they privilege is immutable data, right? So here you would see that in Rust, everything by default is immutable, right? So if you let def mode equal false without the mute, the variable will be immutable, right? So they have a whole one of the early sections is talking about mutability, and the beauty of that is that if a variable is immutable, you can't suddenly make the mistake of reassigning the value to it. So I see like many of my early programs, and also programs that I see from junior developers, is it's abundance of variables, right? You have a lot of these variables, and in some code paths they are set up, and other code paths they are not, because it's usually a bunch of loops and a bunch of if. And at the end of the day, you don't really know if it's all the paths are covered correctly. So if the variable is immutable, you actually are encouraged to sell it. It's like a shortcut for that particular expression, and then you use it, right? So the mental effort to remember what's the meaning of this variable is way reduced. So, and it makes you like work harder to structure your code properly, because you will not have the ability to go lazy and then change the value in the middle. That being said, I do use a lot of these too, right? So it's kind of good to have a blend of the two. And I think, and the other stuff here, right? Okay, so concurrent, right? So the stuff that's concurrent goes well with the fact that it's immutable, because these days processors have become much more multi-threadable. Like they have multiple cores, and then even in one core they can use like hyper-threading and stuff. So before you would have a very very powerful CPU, and then you would really just like buy the fastest CPU you can, because most of your code would be like single-threaded anyways. But these days, even if you want to put a lot of money into a CPU, this is going to buy you actually a CPU that has multiple cores. And if you're not running concurrent code, okay, so technically concurrent code is not like parallel code, right? But I think in practice, when you write concurrent code, it's also because you want to scale up in threads. So concurrent, technically you could only write like async code, like Node, which is only using one thread, right? But in Rust, because you can write concurrent code and parallel code, you probably benefit from using both. And running this kind of code is tricky because uh, as a thread goes, well, you have more than one thread, and they share the same resources, specifically like the share values. There's a risk that if one thread is changing the value, the other thread is suddenly gonna see some value, or worse, if they change the value at the same time, we have no idea which one is going to be getting the right value. So there are two classic ways to work around that, like with mutexes, with semaphores, these synchronization primitives. But it has always been pretty tricky, and then you could you could end up doing the opposite. I mean, you could end up locking so much that you have effectively only like one thread working on a single time, or you could have a similar problem like that. The worst is a deadlock, right? So the program is stopped because one thread is waiting for a lock that the other thread is not relinquishing because he's also waiting for another lock on the first one. Right? This happens quite often if the program is not well structured for multi-threading. So enough that there's been a lot of research in languages to find better primitives for concurrency. And one of the new concepts, well, not very new, but one of the higher way to write multi-threaded programs centers around the fact that if you have a value that is immutable, so you know that the compiler can know that it's never going to change, then it's by default going to be, you can share it. And then you have all this stuff like actor-based concurrency or channels. They work very well. So in Rust you do have that as part of the language. Let's see, where is it? Oh, yeah. And they do have a section, I think, about fearless concurrency. It's a good kind of funky name. Yeah, fearless concurrency. So this is a very funky name. Why fearless concurrency? I think it's basically because they want you to use. Oh, it's right here. Okay, so they want you to write concurrent code, but not be afraid that running this code will introduce bugs that are very hard to find, right? Which is really the case without these kind of constructs. Yeah, so much that in practice, many companies would just not dwell with concurrency. They would just say, okay, buy a faster computer, because the cost of having your program crash or your program hang is much higher than actually buying better hardware. But there's always a limitation to this. You can't keep on buying stuff, throwing money at it. So the fact that the language provides a good mechanism to write concurrent code and refactor concurrent code without introducing bugs is a very good selling point in my opinion. Alright, so we have that. This is another reason why I kind of like this. And then you have this stuff. Generic. Well, generic is cool. Wouldn't say it's this major selling point. Generic is basically saying that if you have a function that takes a particular type, and then it can operate independently from the exact type you want, provided that type has some properties, then you can have that code automatically adapted to these different types. So for example, even like in this code here, this binary operator, we take a function, and that function is anything that is any function that takes a value and returns this stuff, right? Um, in Java, generic code is done pretty differently than in Rust. In Rust, you would have this function actually you really use as a template, as in C++, meaning that this function, if there is no usage of it, will not even exist. And if you have different usage of it with different types, the function will be created multiple times, um, and then the type will be squeezed in. So, for example, if you the difference becomes meaningful if you have containers that are generic. If you have a list of integers and a list of double, also vector, an array of integers and an array of double, what you would like to have is actually the integers. Like integers, for example, is only like 4 bytes. So if the array has 2 elements, you would use 4 times 2, 8 bytes. But if it's a float, it's 8 bytes, so it would be 8 times 2, 16. So basically, you would want to have the container really adapt to the element type that it is containing. Whereas in Java, the container itself, the implementation of the list, which is generic over its type, is actually only generic because it's using references for all the elements. So it's not actually containing the elements, but it's containing a pointer to the element, and that means that they can't have only one implementation for the list, because the list is just a list of pointers, right? When you start adding the elements, it's the logic of adding element is the same because they're all pointers to something, and it's only when you start using the elements that the difference comes, right? Whereas if you have the list in C++, a list of integers is very different than a list of floats because the element size will be different, right? Even if you do that in C, you would have like a bunch of size of operators, and then you have to do the code will be different to account for the fact that the elements are not the same size. So it's really the philosophy that you should get what you should get what you want, and not try to well, I don't know if it's really makes sense, but if you want a list of int, then it's a list of int. If I wanted a list of reference of ints, then I would instantiate a list of references to ints. Right? And structured, I think is very common. It's just that you have you have if then else recursion, so everything is pretty much structured. So I think it covers like one of the main reasons is that it's a system language. Then I think the other main reason, or the second one, is the safety part, which we just talk a little bit about when it comes to concurrency, immutability and concurrency. But I think it goes is much bigger than that because the concurrency stuff is for part of concurrent code, but you can still have lots of issues with in C, even though you don't do concurrent code, and that mainly has to do with memory management. Right? So memory management is like major problems of major source of bugs. So much I think lately, lately Microsoft said that 70% of their bugs, was it really 80? I think 70% of their bugs across the board, across every product they have, and and Codebase is about memory management. So we're going to talk about this later. Okay, so cliffhanger now. We're going to talk about memory management next time.